Welcome everyone again to today's webinar. As Marietta said, the topic for today is an introduction to flow measurement. My name is Terri Leonard and I am a chartered chemical and process engineer with over 9 years experience working in flow measurements with the National Engineering Laboratory. The contents of today's webinar will include measurement fundamentals. We will discuss why measurement is important. I will then introduce the UK National Measurement System and then cover important concepts related to measurement such as calibration, uncertainty and traceability. Once we have covered measurement fundamentals, I will then cover more specifically flow measurement, the fundamentals of flow measurement, some examples of flow metering technology, some of the traditional flow metering technologies available, as well as the more modern technologies. A very brief overview of multiphase flow measurement and the general principle. Once we've covered all of that, we will then be able to discuss the considerations for flow meter selection, and then finally concluding with summary and some questions and answers at the end. So firstly, very briefly, an overview of the company that I'm working for, the TÜV SÜD National Engineering Laboratory, based in Scotland and the UK. As the holder of the UK's national standard for flow and density measurement, we are a global centre of excellence for flow measurement and fluid flow. From our Scottish office and laboratory, we provide independent consultancy, calibration and testing, research and development, and training and knowledge transfer services to industry, including webinars, of course, that we're doing today. The National Engineering Laboratory is part of the TÜV SÜD Group with headquarters based in Munich in Germany. So let's firstly discuss the importance of correct measurement and why measurement is important. Measurement is everywhere and plays a vital role in our lives. Could you imagine carrying out the following activities without correct measurement? Catching a train without the measure of time, buying petrol without measuring the quantity. Would you take medication if the dosage wasn't known? Building bridges or aircrafts require measurement precision. And more importantly, how can we measure a pint of beer or ensure that we do indeed get a full pint at purchase without measurement? It's fair to say that our lives would become chaotic in the absence of a commonly adopted measurement system in place. Measurement provides structure and removes chaos. It ensures open and fair markets. Measurement plays an important role in the UK economy. UK total trade in the last calendar year equated to £1,299 billion. When we trade, we measure, and the international trading system relies on these measurements being right. For most purchases, for example, when purchasing petrol, it's virtually impossible for the consumer to check the quantity that they're paying for, and so it's important for there to be controls in place to protect the consumer. There is a need for an agency responsible for the legislation that governs the fairness of these transactions. This agency in the UK is known as the National Measurement System. Correct and traceable measurement is fundamental to industry, technology and innovation. To facilitate this, the UK requires a regulatory framework based upon measurement confidence. The National Measurement System provides the UK with an infrastructure of laboratories that deliver world-class measurement science and technology. The laboratories provide traceable and increasingly accurate standards of measurement. The National Engineering Laboratory is one of the lead organisations in the UK's national measurement system. The national measurement system represents the position of UK measurement internationally and enables the UK to compete in global trade and manufacturing by ensuring consistency and recognition of measurement units and standards. The national measurement system is delivered through the Department for Business, Energy and Industrial Strategy. So we've covered the national measurement system, and I will now discuss important concepts related to correct measurement, such as calibration, uncertainty and traceability. The network of laboratories of the National Measurement System provides calibration services. But what do we mean by calibration? Calibration is defined as a set of operations that establish, under specific conditions, the relationship between values of quantities indicated by a measuring instrument or measuring system and the corresponding values realised by standards. So, for example, the National Engineering Laboratory holds a standard for flow measurement. We calibrate flowmeters. The reading that the flowmeter gives will be compared to the standards which we hold, and the performance of the meter can then be determined. This is the same principle when calibrating not just flowmeters, when calibrating mass or length or time for any measurement that is made. There is a calibration process against a standard. It's a common misconception that measurement is an exact science. In fact, all measurements are merely estimates of a true value being measured, and the true value can never be known. An estimate implies that there is some degree of doubt about the accuracy of that measurement. All measurements, therefore, have associated uncertainties. Uncertainty of measurement gives an indication of the quality or reliability of a measurement result. The most important point to note when discussing the uncertainty in measurement is that accuracy and uncertainty are very different terms. Accuracy is a qualitative term with no numerical value. Uncertainty is a quantitative term. To fully express the result of a measurement, three numbers are required. The measured value, which is simply the figure indicated on the measuring instrument. The uncertainty of the measurement. This is the margin around the indicated value, inside which you would expect the true value to lie. The measurement uncertainty can be expressed in a relative or absolute basis. And thirdly, the level of confidence attached to the uncertainty. In industry, the confidence level is usually set at 95%. For example, if we have measured a mass to be 1 kilogram plus or minus 10 grams within a 95% confidence level, what we're saying is that we are 95% confident that the true value lies between 990 grams and 1,010 grams. 1 out of every 20 readings will lie out with the uncertainty margins for a 95% confidence level. The wider the uncertainty limits, the more confident we can be that the true value lies within the limits. Achieving low uncertainties in measurement can be challenging and expensive. The measurement application should be considered in selecting the necessary measurement uncertainty. For example, if we consider the financial exposure resulting from a 1% uncertainty in measurement for the purchase of 1 kilogram of tomatoes versus 1 kilogram of gold. 1 kilogram of tomatoes costs roughly £2 per kilo. A 1% uncertainty in measurement equates to plus or minus 10 grams, with an associated cost being plus or minus 2p. This sounds reasonable, and therefore a 1% measurement uncertainty may be fit for purpose when weighing tomatoes. However, 1 kilogram of gold costs roughly £37,000. A 1% uncertainty in measurement of plus or minus 10 grams this time equates to plus or minus £370, a substantial sum of money. Therefore, we would desire a lower uncertainty when measuring gold. The third important term related to fundamentals of measurement that we will cover today is traceability. Traceability refers to an unbroken chain of comparisons relating an instrument's measurements to a known standard, each having a stated uncertainty. Calibration to a traceable standard can be used to determine an instrument's precision and accuracy. The National Measurement Institutes and holders of the national standards provide the highest level of standards for the calibration and measurement traceability, and they sit at the top of the traceability chain. Each step of the calibration chain will have an uncertainty becoming smaller at each step as we trace back to the national standards. Although the end product will be traceable to national standards, it's important to note that the uncertainty associated with the instrument will be significantly larger than the national standard laboratory. So now that we have briefly discussed the fundamentals of measurement, let's now look more specifically at the fundamentals of flow measurement. So why would we measure flow? There are many applications where flow measurement is necessary. Flow measurement is vital for taxation, custody transfer and allocation in the trade of oil and gas. Oil and gas being lucrative commodities, and therefore accurate flow measurement is important, with more focus on achieving lower measurement uncertainty within the oil and gas industry. Across many industrial sectors, there are safety and environmental regulations which exist, making flow measurement necessary to ensure specifications or requirements are being met. What measurement is required? This is an important consideration when determining a flow metering technology to suit any given application. So the application of interest will determine the type of flow measurement required, and therefore will then enable a suitable flow meter to be selected and specified. Whether that be a measure of velocity, perhaps a direct mass flow measurement is required, or a volumetric flow measurement, for example. The thermophysical properties of the fluid being measured are vitally important for flow measurement. Knowing the fluid density allows conversion between mass and volume. The majority of flow metering technologies measure volumetric flow, and therefore converting to mass, knowing the fluid density, is critical. Immiscible fluids such as oil and water result in the lighter or lower density fluid floating on the top. Gravity separators are therefore utilised widely in the oil and gas industry for the separation of oil from the water. The sizing of the separators requires knowledge of the fluid properties, including density. Fluid viscosity is a measure of the resistance of the fluid to being deformed by shear stress. In simple terms, fluid viscosity is an expression of how thick the fluid is and relates to the fluid mobility. The image shown is of a highly viscous fluid. Liquids and gases behave very differently, with the viscosity of liquids decreasing with temperature and the viscosity of gases increasing with temperature. Surface roughness, or pipe roughness, causes friction that impedes the flow at the pipe walls, resulting in the characteristic velocity distribution or velocity profile that we will discuss in an illustration shortly. Compressibility is another important term for consideration. Compressibility being defined as the fractional decrease in specific volume caused by a unit change in pressure. Gas is highly compressible, and this affects both the behaviour of the fluid and the properties of the fluid, with gas density increasing with pressure due to its compressibility. Liquid is much less compressible, and for many applications, it's fair to assume that it's incompressible. Liquid compressibility, however, can still be important to account for in fiscal applications, for example, where low measurement uncertainty is required, particularly at elevated pressure, where it is no longer fair to assume that oil, for example, is incompressible. Reynolds number is the most important dimensionless number in fluid mechanics and is the ratio between viscous forces in a fluid and inertial forces. The inertial forces are a function of fluid density, velocity, and pipe diameter. A fluid in motion flows in layers, and shear is created at the pipe wall as the fluid encounters viscous resistance due to the surface roughness that we mentioned earlier. And this creates a flow profile or velocity profile as shown on the screen for laminar flow conditions. At increased velocities and higher Reynolds numbers, the inertial forces dominate and the layers of fluid travelling through the pipe begin to roll past each other, creating a turbulent flow profile. The magnitude of the Reynolds number is used to characterise the flow as laminar or turbulent. Laminar flow, where viscous forces dominate, occurs for Reynolds numbers below 2000. There is a transitional region where the flow switches back and forth between laminar and turbulent, and this occurs roughly for Reynolds numbers between 2000 and 4000. Above 4000 Reynolds number, we are then in the turbulent flow region, and this is the most common for most industrial applications. An important consideration for flow metering and the selection of a suitable flow metering technology is installation effects. The impact that installation effects could have on the performance of flow meter and the flow metering technology varies depending on the particular technology selected. Valves, bends and reducers disturb the flow and the velocity profile of the fluid, resulting in a skewed or asymmetric profile, which will take a length of straight piping to recover fully back to a fully developed flow profile downstream. So for many metering technologies, the importance of avoiding disturbances immediately upstream and downstream of the meter cannot be overlooked. Large measurement errors can be expected due to installation effects and a disturbed or skewed flow profile through the meter. As I said, the impact of installation effects on metering technologies is different depending on the meter that has actually been selected and installed. Some metering technologies are more affected by installation effects and flow profile disturbances than others, and we will discuss that a bit further when we look at some examples of flow metering technology that is available. So we have now covered the fundamentals of flow measurement. We can now look at some specific examples of flow measurement technology. There are many types of flow metering technologies available for a range of different applications. We have separated the flow metering technology into two categories that we will cover and discuss today, being traditional flow measurement technologies, such as differential pressure meters, positive displacement meters, and turbine meters. And I'll also cover some of the more modern technologies now available, including the Electromagnetic Meter, the Coriolis Meter, and the Ultrasonic Meter. So firstly, differential pressure meters or DP meters. Differential pressure meters remain the most common meters in use worldwide today across a range of industrial sectors and applications. They are very simple to make and normally without any moving parts, which is a great advantage of the DP meter. But because they have been developed and thoroughly researched and characterised over the years, they are very well understood. Differential pressure meters also have accepted international standards based on the years of research that has been carried out. And examples of DP meters include the Venturi tube and the Orifice Plate. The Orifice Plate is the most common DP meter. Differential pressure meters operate by partially obstructing the flow. They all operate on the same basic principle. So, partially obstructing the flow, which then creates a difference in the static pressure between the upstream and downstream of the device. The beta ratio is the ratio of the pipe diameter, denoted here as D1, and the diameter of the obstruction, D2. The diameter of the orifice in the case of the orifice plate. The mass flow through the differential pressure meter can then be calculated from differential pressure measured through the meter, knowing the fluid's density and the beta ratio. The governing equations that are appropriate for differential pressure meters are well documented, and as well as the limits of use in the standards available. The discharge coefficient, CD, accounts for frictional effects and has again been well characterised for each DP meter available through years of research and development. Differential pressure meters such as the Orifice Plate can generally be used without flow calibration, which is one of the main advantages. Another type of metering technology, a very common type of single-phase metering technology, is the turbine flow meter. And the turbine meter is used for high accuracy measurement of both liquids and gases. There are different designs depending on a liquid application versus a gas application for a turbine meter. A turbine flow meter consists of a multi-bladed rotor mounted on bearings, allowing it to rotate as it is driven by the flow. This gives a flow meter where the speed of rotation of the rotor is proportional to the volumetric flow rate of the fluid passing through it. Counting the number of rotations and the frequency of pulses per second gives the flow rate, and the total rotations gives quantity of flow through the meter or the total volume of fluid. Turbine meters, as I said, are available for both liquid and gas. They are, however, susceptible to disturbances in the flow profile, and so for a turbine meter, they do require what's recommended is a minimum of 30 diameters of straight piping upstream of the meter for a fully developed flow profile for optimal performance, or use of a flow straightener. Positive displacement meters, another common type of single-phase metering technology, operate by allowing the fluid to flow through the meter, capturing a volume briefly before discharging, and then counting the amount of volumes that have passed through the meter to get the flow output. In this respect, a bucket lifting water out of a pool, counting the number of times that we carry out that operation, timing the operation, and knowing the volume of the bucket is a simple positive displacement meter. There are a few examples of PD meters listed on the screen. The diaphragm meter is our typical domestic gas meter, and the oscillating piston meter is commonly used for domestic water metering. General characteristics of positive displacement meters include they are generally accurate. They can, however, be quite bulky and complicated. Because they consist of mechanically moving parts that intrude into the flow, they can cause problems with blockages if they fail. They are good for batching applications, and they are less susceptible to installation effects than other types of metering technology available. The oval gear meter is an example of a PD meter, which has two oval gears which mesh together as they rotate. They have minimal clearances and are suitable for highly viscous fluids. They aren't, however, suitable for lighter oils, as the gears require lubrication. The electromagnetic meter, or commonly known as the mag meter, is an example of a volumetric flow meter which doesn't have any mechanically moving parts and is ideal for wastewater applications. Mag meters are also ideal for applications where low pressure drop and low maintenance are required, as long as the liquid is conducting, as the operation of an electromagnetic flow meter, or mag meter, is based upon Faraday's law of induction, which states that the voltage induced across any conductor as it moves at right angles through a magnetic field is proportional to the velocity of that conductor. So another example of our modern flow metering technology is the Coriolis meter. The Coriolis meter is becoming much more common in industry now and offers a very high accuracy option for flow metering. The main advantage of a Coriolis meter is the fact that it offers the ability of direct mass measurement as well as independent density information. A Coriolis meter consists of a vibrating flow tube through which the fluid passes and an electronic transmitter which monitors and maintains the flow tube oscillation by generating a suitable drive signal. In the absence of flow, the inlet and outlet sections of the flow tube vibrate in phase with each other. A phase shift between the inlet and outlet sections occurs when the fluid flows through the vibrating flow tube, which is directly proportional to the mass flow rate of the fluid. Two sensors monitor the flow tube vibration as the process fluid flows through. The electronic transmitter collects the sensor signals and carries out the mass flow and density calculations. The exact frequency of the flow tube vibration depends on the density of the fluid and can be determined by measuring the frequency of oscillation of the tubes. Coriolis meters are now also being used for density measurement as opposed to mass measurement, and are actually, in some applications, the preferred choice over densitometers. They can be used to monitor contamination in oil and water mixtures, for example, and this is something that we also are carrying out here at the National Engineering Lab, using Coriolis meters for their density output as well as direct mass measurement. Our last example of our modern types of single-phase metering available is the ultrasonic meter. Ultrasonic meters use sound waves to determine the velocity of a fluid flowing in a pipe. At no flow conditions, the frequency of an ultrasonic wave transmitted into a pipe and its reflections from the fluid are the same. At flowing conditions, the frequency of the reflected wave is different due to what is known as the Doppler effect. The difference in frequencies transmitted and received are proportional to the fluid velocity. Depending on the application and type of ultrasonic metering technology selected, the transducers can be arranged in different ways. The capability of non-invasive measurement is a benefit and advantage for the ultrasonic meter when compared to traditional metering technologies. They also have no mechanically moving parts, which is another advantage, as they are therefore not susceptible to damage. Ultrasonic meters do require a well-developed velocity profile for optimal performance, and again, 30 diameters of straight piping upstream is recommended as a minimum when using an ultrasonic flow meter, although a flow straightener could be used or considered as well for optimal performance. Ultrasonic meters are available for liquid and gas applications. Okay, so we have now covered examples of traditional and modern single-phase metering technologies. Let's now briefly discuss multi-phase flow measurement and the general principle. Multi-phase flow within the context of the hydrocarbon production industry concerns the simultaneous flow of oil, water and gas mixtures within the same pipeline. Solids and other components can also be present, such as sand or wax. Oil, water and gas mixtures are often described as three-phase within the industry. Technically speaking, the flow is actually multi-component as opposed to multi-phase. The flow is in fact, of course, two-phase, as we have liquid and gas. Multiphase flows are most commonly characterized by volumetric flow rate ratios of oil, water and gas phases. Due to density differences between the gas and the liquid components, gas flows along the top of the pipeline, being the lightest component, and since oil is lighter than water, water flows along the bottom of the pipeline due to gravity. The ratios of oil, water and gas, as well as characteristics of the flow, can change dramatically, resulting in different degrees of mixing and distribution of the phases. This causes different flow patterns or flow regimes to develop. Multiphase flows can also be characterized by their flow pattern. An illustration of a horizontal flow pattern map is shown on the screen. It's important to note that flow pattern maps are not general and vary as a function of pipe diameter and fluid properties, as well as many other variables. Different flow patterns result in a vertical orientation, and vertically oriented multiphase meters are most common due to improved mixing and distribution of the phases. So the general methodology of multiphase flow meters. Multiphase metering technologies are required to measure oil, water and gas flow rates within a multiphase mixture simultaneously. The total bulk flow rate of the mixture is required, and common methods for the measure of the bulk flow rate of the mixture include the use of differential pressure devices such as a Venturi meter. The Venturi meter is the most common type of measure of bulk flow rates of multiphase metering technology. Positive displacement meters could also be used, however are far less common in multiphase metering technologies available in the market today. And cross-correlation techniques have also been used and could be considered for bulk flow rate measurement of the mixture. Secondary sensors must also be used in order to measure the individual phase fractions of the multiphase mixture in addition to the measure of the bulk flow rate. In order to determine the individual phase fractions, a number of methods could be used, such as the gamma ray absorption technique, which gives an indirect measure of the density of the phases, or the use of sensors which measure the electrical properties of the fluid, and microwave techniques, taking advantage of the differences in permittivity and conductivity of the oil and water phases. Knowing the phase fractions of oil, water and gas, as well as the bulk total mixture flow rate, individual flow rates can then be calculated. So now that we have covered the fundamentals of flow measurement and some examples of metering technologies, we can then start to discuss and think about considerations when selecting a suitable flow meter for a given application. So how do we determine the most suitable flow meter for the given application? Questions which should be considered when selecting a flow meter for any specific application includes what output is required, as we mentioned earlier. Is a direct mass measurement necessary, in which case we discussed the Coriolis meter provides a direct measure of mass, volumetric flow, or perhaps density. The type of fluid being for a liquid application or a gas application, or perhaps for a multiphase metering condition. The fluid type as well as the fluid properties are necessary in order to specify an appropriate flow metering solution or technology. The operating conditions as well are important. The rangeability required for the meter or the turn-down ratio. All metering technologies have different turn-down ratios, and so the sizing of the meter as well as the number of meters required for the application will result from the turn-down ratio, as well as the temperature and pressure range. The operating environment as well as the operating conditions is important for consideration. Uncertainty requirements often links to the budget available and the importance of the measurement. We may be targeting a very low measurement uncertainty, however the budget and the importance of the measurement may be conflicting. There may not be enough budget to implement the solution that is initially desired for the measurement uncertainty. And also installation and maintenance requirements. So I briefly touched upon installation effects, and these affect different metering technologies, require different upstream and downstream lengths of straight piping for installation. So the flow meter selection process is often a compromise. In summary, measurement underpins virtually all key processes across an extensive range of industrial sectors. Correct, traceable measurement is essential to our economy. There are numerous technologies available to provide flow measurement. We covered some examples of single-phase metering technologies, from the more traditional methods to the new modern methods that are available, and the general principle of multiphase metering technologies. Selection of flow metering technology requires a thorough understanding of the application and the measurement environment. Overall, I hope that the webinar has provided an appreciation that measurement underpins virtually all key processes across an extensive range of industrial sectors. Thank you for your time in attending today's webinar, and please submit any questions that you may have.
Okay, thanks very much for that, Terri. If you just bear with us for a couple of moments till we bring up some questions. I think we've maybe got time for two or three questions, and we'll hopefully be finished quite soon. In the meantime, while we're waiting on the questions, we've put up a list of some forthcoming events, and you'll see we've got a webinar taking place next month as well. So if you're at any of these events, we will be there, so feel free to pop along and say hello. Right, if you just bear with us, let's see if there's any questions. Is there any there, Terri, that you want to pick up?
Okay, so there's a question here which someone has asked regarding the uncertainty of measurement. What is the procedure for determining the uncertainty of my measurement? The establishing and determining measurement uncertainty is an in-depth process, and there is a developed standard available which details the process and the procedure, known as the Guide to the Expression of Uncertainty, or the GUM for short. So in order to determine the overall uncertainty associated with your measurement, you first have to list all possible sources of uncertainty which feed into that measurement. You then have to determine the associated uncertainty for each input source, and there's a process for combining all of the sources of uncertainty by a process known as the root sum square method. The uncertainty can therefore be stated in the way that I discussed earlier. So with the measured value, plus or minus the determined uncertainty associated with the measurement, and stating the confidence level that has been selected. So there is a detailed procedure available for the calculation of uncertainty of measurement, but it is an in-depth, involved process, and it's something that we do provide, and we do carry out here at the National Engineering Laboratory as well. So I'm just looking to see if there's any other questions. So there's another one here, which is, why are DP meters, differential pressure meters, commonly used for multiphase applications? The simple reason, or the main reason for that, is that differential pressure meters are very robust without any mechanically moving parts. So for a multiphase application where different flow patterns develop, which can damage any mechanically moving parts, so for example a turbine rotor will be damaged very quickly in a multiphase flow application, whereas a differential pressure meter is very robust, for example the Venturi tube, and that is the main reason why it is used more commonly as the core for bulk measurement of multiphase, for multiphase applications. It's also very simple in its operation and the fundamentals. It's well understood. However, one important point to note is that although I mentioned earlier that differential pressure meters are well characterised, that is related to single phase applications, as are the standards that are available. But for multi-phase applications, the correlations and models that have been developed by the vendors themselves for multi-phase metering applications. So the standard doesn't comply with for a multi-phase application. Okay.
I think we've just got time for one short question.
No problem. So the last question that we'll cover just now is there's a question here, why the uncertainty of the end product is significantly higher than the national standards laboratory. So that was related to the traceability chain that we discussed earlier, and in the example, the uncertainty stated for the national standards lab was 0.05%, and the end product was significantly higher. I think it was stated at 5%. So the reason for that is that the uncertainty statement from the national standards lab will include all of the input uncertainties associated with the calibration process. So during the calibration of the flow meter, for example, but as soon as the flow meter is then removed from the calibration facility and installed in its application, there are then many more sources of uncertainty that have to be accounted for. One being the drift of the meter between calibrations, for example. There may be additional sources of uncertainty to account for if the conditions of use are different from the conditions during the calibration process. So it's not possible to get an uncertainty of measurement of your device better than the reference for the National Standards Laboratory.